How can RL agents overcome poor sample efficiency? Imagine trying to learn a new game but having to play hundreds of times just to get the hang of it. That's what poor sample efficiency looks like in reinforcement learning. It means the agent needs lots of interactions with its environment to learn good policies, which can be slow and costly. In real-world applications like robotics or autonomous vehicles, this can be a big problem because time, money, and safety matter. So how do we make these agents learn faster with fewer tries? One way is through experience replay. Think of it like watching your favorite sports highlights repeatedly. The agent stores past experiences, including the current state, the action it took, the reward it received, and the next state. By reusing these experiences during training, the agent can learn from rare or important events multiple times without needing to interact with the environment again. This boosts learning speed and makes better use of limited data. Another approach is model-based reinforcement learning. Instead of just learning from real interactions, the agent builds an internal model of the environment. This model predicts what might happen next based on current actions. The agent then uses this model to simulate future states and rewards, allowing it to plan ahead. This way, it can learn from imagined experiences, reducing the number of real-world trials needed. Off-policy learning is also helpful. Here, the agent learns from data generated by previous policies or even demonstrations from humans or other agents. This broadens the data sources and speeds up learning because the agent isn't limited to only its current behavior. It can reuse old data to improve faster. Reward shaping is another trick. By adding extra guidance or background knowledge, the agent gets a clearer idea of what behaviors are good. For example, using large language models to provide context or hints helps the agent understand the environment better, making learning more efficient. Adding auxiliary tasks is like giving the agent side missions. These tasks, such as predicting environment features or reconstructing inputs, help the agent develop richer internal representations. This extra learning support allows the main policy to improve more quickly, especially in complex situations. Smart exploration strategies also play a role. Curiosity-driven methods encourage the agent to explore new or uncertain states. This helps discover valuable information faster but needs to be balanced, so the agent doesn't waste time on irrelevant or risky areas. Finally, some algorithms adapt to the difficulty of specific tasks. They focus on easier instances first to speed up learning, while still maintaining performance on harder parts. All these strategies work together to help reinforcement learning agents learn faster and more efficiently. They make training more practical for real-world uses like robots, self-driving cars, or game AI. Using tools like synthetic data generators or environment simulators can also support these methods, making the process smoother. Improving sample efficiency is not just about saving time and money. It also reduces the environmental impact of training large models. It means fewer experiments, less energy, and safer deployment in physical systems. So, by combining memory reuse, environment modeling, guided learning, and exploration, we can help reinforcement learning agents become smarter with less data.